Okay, so today we will be dealing with surface integrals. So the big title is surface integrals, but to do so, we start with surface parameterization. Remember, when we started double integral, just to remind you, when we started the line integrals, we defined this using curve parameterization. What was the curve parameterization? What was the curve parameterization? The main idea behind curve parameterization, we write the equation as r of t equals something like this: x of t, y of t, if you're dealing with two variables in R2, but if you have a third variable, you just add the third coordinate z of t. And the t values, this is the idea, the t values are between alpha and beta. So you have one dimension line like this. This represents the t. The t is between two values, alpha and beta. This parameterizes a curve. So the curve in general can be a circle. It could be something like this. It could be anything arbitrary like this. Not necessarily a closed curve. It could be like this. This is the curve. So this is a sample of what curve we can have. So the idea was you have a straight line, a line segment. Through the parameterization, if you apply this parameterization, the r of t, this equation, then this r of t has the capability of converting this line segment into a thread like this, or like this, the circle, and so on. So it's like bending the line segment into a curve in a certain way. So without doing any math, imagine you have a thread like this, and you're asked to convert it. You're asked to convert it to a circle. Can we do it? Yes, we can. Can you bend it to get something like this? Yes, we can, and so on. But the question is, imagine you have a thread like this. So this is a line segment from alpha to beta. It could be from 0 to infinity. It's not necessarily a finite interval. But imagine you have a line segment like this. Can you bend this line segment to get, for example, a disk? What do we mean by a disk? A disk is a solid circle. So imagine you have a line segment, a thread. Can you bend it in any way to get a disk? There is no way. If you get it, something is wrong. Can you bend it to get something like this? There is no way. So for now, we can just say that a line segment cannot give any surface. So what do we mean by a surface? A surface, it's something with an area. It is something with an area. A curve, it is like some deformation of a thread. It is just a line segment, deform it in any way you like. That's called a curve. Now a surface, basically you start with a plane or a portion of a plane, which what we call planar region, and deform this in any way to get a surface. So for example, this is a planar region. The rectangle or the square is a planar region. Can you deform it to get, for example, a cylinder? Yes, we can. Just bend it this way, imagine it, you will get a cylinder. So the idea now for surface parameterization, what is the idea? The idea is that you needed a rectangle to get a cylinder. So the idea in general, we need a planar region to form a surface. A planar region, that means we need two variables. So the idea, you can't have one variable, you can't start with one variable to get a cylinder. You can't start with one variable, there's no way you start with one variable to get a rectangle, there is no way. Or to get a circle, there is no way. So all of this is wrong. There is no way you can get this. So what's the exact definition? What is the definition of surface parameterization? Let's see. First of all, what is the equation of a surface? What is the equation of a surface? In general, a surface is something in R3. So let f, x, y, z equals 0 be a surface. In general, it is in R3. But again, surfaces, I can look at disks like a surface. And I can look at disks as surfaces. For example, if this disk is placed in R2, I can look at it as in R3, but with the z coordinate equal to 0. So imagine you have an equation that represents a surface. A surface parameterization of the surface S with equation f equals 0 is R, but this time the R depends on three variables. It depends on two variables, but it has three coordinates. So this is let's say x, this is the first coordinate, so x of uv, y of uv, and z of uv, so that f of r of uv equals 0. So f of r uv equals 0, that's the first equation of the surface. This is the surface of the equation. When we write our parameterization, we assume the x coordinate to be this is the y, this is the z. The three coordinates are given by r, so basically the original equation for the surface is equivalent to this form. So simply, we just find the three coordinates in terms of two variables, u and v, which satisfy the given surface equation. To make it clear, let's take an example. So for example, let's find a surface parameterization of the disk. So I'm taking the disk. Let's call it D, for example. What is D? I'm taking x, y, 0, such that x squared plus y squared is less than or equal to 1. First of all, what is this? So we are talking about R3. X squared plus y squared equals 1, that's the unit circle. Less than or equal to 1, so we're dealing with the unit disk. So when z is 0, that means on the xy plane, down, on the xy plane, you have this unit disk. This is the unit disk. So this is a surface. It is something with an area. Now we need a parameterization. How do we find a parameterization? Simply speaking, the parameterization is some equation, a vector equation, in three variables. The three variables must satisfy the equation of the disk. What is the equation? In fact, it's not an equation in this example, it is an inequality, less than or equal to 1. So what we need to do is to write three coordinates so that the three coordinates cover all the points. They give you all the points on the surface. We're dealing with a circular region, so maybe if we try u cosine v, u sine v, and 0. So we're dealing with polar coordinates. If you like, you can write it in terms of r and theta. U as r, So it's r cosine theta, r sine theta, and 0. Now in this case, what are the theta values? The theta values are, you are doing it as a full rotation, full circle. So the theta is between 0 and 2 pi, and the r, the radius, is between 0 and 1. The idea is exactly like this. So if you draw, the parameterization depends on two variables. So if you draw R2, but this time what are the coordinates in R2? The coordinates are R and theta. Then you have your surface in R3 here. The idea, if you take theta between 0 to 2 pi, so the y-axis 0 to 2 pi, the r 0 to 1. So basically, we are talking about this region. If you take all points, so that the theta is between 0 and 2 pi, the r are between 0 and 1, basically this is what you get. You get this rectangle. Now what is the role of the parameterization? So what's the meaning of this equation r of theta equals r cosine theta, r sine theta, and 0? The idea is this equation converts or deforms or bends this rectangle to make it exactly like this. How? So this is done using R. But how can we visualize this? How can we see? How can we look at this rectangle as a deformation of this unit disk? The idea is like this. So I'm going to draw them together. So again, this is my rectangle. This is my disk. What is the idea? I am moving this to this through R. The idea is this. If you take this line, this is a line segment. For this line segment, theta is 0. But what are the R values? The R values, they range from 0 to 1. So basically, if you go back to the parameterization, this is the parameterization. R of r theta equals r cosine theta, r sine theta, and 0. So when theta is 0, what do you get? What is r of r0? If you substitute here theta 0, what do you get? You get r cosine 0, which is just r. You get 0, you get 0. So as r goes from 0 to 1 here on the y-axis, on the x-axis, sorry, what you get on the disk is all points are 0, 0. What is the meaning of that? And r is between 0 and 1. So this is the x-axis, y-axis, z-axis. The y and the z are zeros. You're not moving in the direction of the y or the z, but you are moving in the direction of r. So basically, this line segment here in the xy plane, it gives you exactly this line segment. This line segment. So this line here from the rectangle covers this line from the circle. For example, imagine you take another line like this, any other line. So imagine theta is just a fixed value in 0 to pi. Then what do you get? So let's call it theta star, just to distinguish from theta as the arbitrary variable. So what is r of r theta star? It is r cosine theta star, r sine theta star, and what? And 0. And the theta star is fixed, and the r is from 0 to 1. So basically, what is this? These are the polar coordinates, r theta star, right? So if you look at R2, you have the angle with the x-axis theta star, and this is r. This is the meaning of r cosine theta star, r sine theta star. So basically, if you copy this to there, what is it? So you have theta star with the positive x-axis, and the r is moving from 0 to 1. So you are covering all this line segment. So the idea now, I think the idea now is very clear. The idea now, if you take any line segment here from the rectangle, it moves using this parameterization and gives you a certain line segment like this, like this, like this. So horizontal lines here, horizontal lines, they are moved to radials. This is the way we can look at the rectangle somehow as another form of a disk. So in general, this is the rectangle. Take every line segment, start with the origin, and do it that way as radials. That gives you the unit disk. This is how we can look at this parameterization. In fact, so another way to look at r of r theta equals r cosine theta, r sine theta 0. So again, my parameterization it takes this rectangle to this disk. Now, we already saw how those line segments, the horizontal lines, are mapped into radials so that the rectangle becomes a disk. Now, the other way to look at it, what about if you look at this rectangle and you take vertical line segments like this? So what happens this time? So for each of these line segments, for each of them, r is fixed, and r is between 0 and 1, but the theta is ranging between 0 and 2 pi. Theta is ranging between 0 and 2 pi. So the idea now again, if you take r of r theta, r is fixed, so let's say r star, so that's r star cosine theta, r star sine theta, and 0. The theta is changing, the r star is fixed. If you look at the first two coordinates, so these two coordinates, what is the square of the first plus the square of the second? That would be r star square. So basically, this is a circle of radius r star, which means each of these line segments, the vertical line segment, is mapped into a circle of radius r star. So for example, if r star is 0, it gives you the origin. That's the meaning of a circle of radius 0. Then as r star increases from 0 to 1, you're getting a circle of radius r star. When r star is 0.1, you're getting a circle of radius 0.1. 0.2, another circle of 0.2, 0.3, 0.3, and so on. So this time, you are getting the disk by circular mappings. Each of these line segments is mapped into a circle. So line segments is mapped into a circle. This is the way you can get a circle or a disk from a solid rectangle. So again, the summary of this example in the end, we have a disk. This is my disk. I can write this parameterization for this disk, but these explanations, they show us how to get the disk exactly from the rectangle.